Hello students, this is lecture 5 of NTH 201. In the last lecture we discussed length of cross product and relationship with area of a parallelogram, direction of cross product, volume of a parallelepiped, and it comes out to be the triple product of certain vectors. We looked at lines in R3 and look at two forms of equations, one in point direction form and other in point form. We also looked at equation of a line segment in R3, plane in R3, angle between planes, and distance of a point from a plane. So today we are going to talk about paths and curves in plane and in space, and also discuss motion of a particle using these concepts. So let I be an interval in R. It could be any kind of interval. It could be all of R. It could be an open interval, closed interval, half open, half closed, anything possible. Okay, so any kind of interval in R. A path in a plane R2 is a function C from interval to R2. Okay, and a path in space R3 is a function C from I to R2. I'm sorry, R3. Okay, so I'll come to that. I will discuss these using the figure on the left. The image of this path given by the collection of points when you vary over t in this interval is called a curve. So if you look at this picture on the left, suppose your interval is this interval AB, closed interval. Okay. Now, this is a picture in R3. So you vary your variable over this interval and you look at the image of this function C. Okay. Suppose this comes out to be this picture here. It starts at CA, which is the image of A under C, and CB, which is the image of B under C. So this function C is called path, and the image, that curve that you see, is called curve. This is a picture in R3, so it's a curve that you get in R3, and this is a path in R3. You can have similar picture in R2 as well. Okay, we'll look at a few examples and it will be clear. So path is a function, curve is the image of that path or image of the function. The path C is called a parametrization of this curve. So when you look at this curve, this path C or the function C is called parametrization of this curve. So you are parametrizing the curve. Also, it is said that the path C is said to parameterize this curve. So either you say that path is a parameterization of the curve or the path parameterizes the curve. Okay. So if I equal to A comma B closed interval, then the image under C of the endpoints A and B are called endpoints of the curve. So in this particular picture, these endpoints that you see in bold, they are actually the endpoints of this curve. If C is a path in R2, that means C will have two coordinates, right? So at every t, CT will be a point in R2, right? So a point in R2 has two coordinates, x and y. So because this is dependent on t, let us have this dependence on t show up here also. So if C is a path in R2, meaning that C takes I to R2, then CT is equal to xt comma yt, where x and y are functions from I to R, and they are called component functions of C. Okay. Similarly, if C is a path in R3, we can write Ct as xt, yt, zt because it will have every point will have 3 coordinates. And these 3 functions are functions from I to R, right? Each coordinate is a real number, right? So they are functions from I to R and they are called component functions of C. Okay. So there are many things that we have defined on this slide. We have defined a path, which is the function. Image of the path is called a curve. The path C is called parameterization. The image of the endpoints of the interval are called endpoints of the curve. And then we define component functions of a path. Right? Okay. Let us look at a few examples. So the first example is a curve in R3 or a path in R3. So a line in R3 through a point P0, which is x0, y0, z0, in the direction V, which is given by components A, B, C, is a curve given by the path C. Here interval is R because a line is stretched in both directions, right? It goes in both directions. So it goes from R to R3 and it is defined as, so you remember equation of a line passing through a point x0, y0, z0 in the direction V. It is nothing but x0, y0, z0 plus t times v. Now this t is the variable that I use here. If you open these brackets, you will get x0 plus ta plus y0 plus tb plus z0 plus tc. Right? So this is the path that gives you this line as the curve. Okay. What are its components? Components are xt equal to x0 plus ta, yt equal to y0 plus tb, and z0 equal to z0 plus tc. One simple observation from this picture is when t is positive, then you are on this side of the line, right? Because v is in this direction. Whereas if t is negative, then you are on this side of the line. And when t is 0, you are at the point x0, y0, z0. Okay. Now let me pose 2 questions that I would like you to think about. So this is a line passing through a point in the given direction, but we also looked at point-point form, right? So the question is, give a path, meaning give a function whose curve, meaning whose image is the line segment in R3 joining these 2 points. Right? So we looked at the equation of a line segment. Now, second question is, give a path whose curve is the triangle in R3 with vertices at these 3 points. Now, let me give you a hint. The second one uses the first question. So, what is a triangle? Triangle is a collection of 3 line segments, right? The first line segment is joining the first 2 points. Second one is joining the second and the third point, and the third one is joining the first and the third point, right? So if you use question 1 to get all those 3 pieces, you just have to put things together as a function. Okay, so I will leave that to you. You have to choose your interval suitably. So you can't use the same interval for all the 3 sides or all the 3 line segments. You have to choose different intervals and then put things together, as domain should be one single interval. Okay. So these 2 will be discussed in the tutorial, but it's worth trying. You should try it yourself. Okay, let us look at another example. which is a unit circle in R2. So this is a curve in R2. Previous one was a curve in R3. So a unit circle in R2 is described by this equation. So I will not get into this. You know that this is the equation which gives you a circle which is shown in this picture. Now this picture can be obtained using the path C from R to R2 defined as Ct equal to cos t comma sin t. So as t varies over R, you get points on this circle, right? Now, there is something that you should notice here, that these component functions cos t and sin t, they are periodic functions, right? Meaning that after every 2 pi they are equal, right? So if I, let's say, take t equal to 0, I am here at the point 1 comma 0. Now when t is equal to 2 pi, I am back at this point, right? So instead of this domain R, I could have taken closed interval 0 to pi. Even then you would get the circle, right? So this is a path whose equation is the same, but domain is something more than necessary. That is okay. There will be a lot of repetitions. All we want is a function which gives you the image as this. Okay, so this is not a 1-1 function. This is not a 1-to-1 function, but it's okay. We are not demanding a 1-to-1 function. So this is also a legitimate path which gives you this curve. Okay. Now let me ask you this question. What is the path described by the curve? Same curve, but when you restrict yourself to the interval 0, pi by 4. What are the values on this circle that are attained when you restrict yourself to this domain? And what are its endpoints? So I'm asking two things. One is what is the I'm sorry, I should have written what is the curve described by the path C. Okay, so first of all, what is the curve that's described and what are its endpoints? Okay. So let us move on to another example, which I will not get into details, but let me explain what's going on. So if you have a point on moving on a rolling circle, okay. So this is a circle. Suppose I start at this point, and this circle is moving, okay, and the circle completes one rotation in 2 pi units. So what happens if you trace out this point as you move here? What happens? So what happens is this point moves according to this curve, where the equation of this curve or the parameterization of this curve is given by t minus sin t comma 1 minus cosine t. One can prove this, and it's possible that you have proved it in your physics courses. Uh, so I will not get into this, but the path that is traced out by a point moving on the rolling circle is this path, and it's called a cycloid. Okay, so after 2 pi, you are back to this picture, and things will be same again. So it will be like this, then like this, and so on. Okay. Now, let us relate the concepts that we have seen with motion of a particle. Okay. So now I would like you to think of Ct as the path traced out by a particle with time t, and let us define the velocity vector and speed. So the point Ct, which is the point in the space, okay, Ct is called the position of the particle at time t, where it is at time t. The velocity of a path C at time t is a vector defined as So this is something that you are aware of. The only difference is now C is a vector. So when you look at this numerator, you are subtracting 2 points, right? So when you're subtracting 2 points, you will get a point. And you divide by h, that means you are dividing each entry of the point by that h, right? And then you take the limit. So when you take the limit, you will take limit component wise. Okay, so C prime t is defined as limit h goes to 0, C of t plus h minus ct by h, and we draw the velocity vector with its tail at the point ct. I will come to this point in a minute. And the speed of the path c at time t is the length of this vector c prime t. Okay, so it is the norm of c prime t, which is the length of velocity vector. Now, if ct is xt, yt, zt, then c prime t is x prime ti plus y prime tj plus z prime tk, and st is the length of this vector, which you know is given by this. Similarly, if your curve, your motion is in R2, this first one is motion in R3, but suppose your motion is in a plane, then you have only two components, in which case C prime t becomes this and st becomes its length, right? So, okay, let me go back. So, so I just told you that you take your velocity vector with its tail at the point ct, right? So let us look at this picture. So this is the curve, okay, and this is in R3. So this is the curve in R3. This is the position at time t. This is ct. When you draw c prime t, it is a vector whose tail is at ct. So that is how you draw the vector. This is your c prime t. Now the question is, how do you define a tangent vector? So at time t equal to t naught, the velocity vector c prime t naught is a vector that is tangent to the curve at the point ct naught. So this vector that you see is a vector that is actually tangent to this curve. So this will be discussed in the tutorial why it is tangent to the curve, but this is what you get. So when you draw the vector c prime t at the point ct, this vector comes out to be tangent to the curve. Okay, what do you mean by tangent? Meaning that it touches this curve at only this point. Okay, so now let us So in this picture, I am saying that it touches here. Okay, there could be other possibilities which we will discuss in the tutorial. For now, this is how your picture should look like. Okay. Now let us define a tangent line. So the tangent line at the point CT naught is given by LT equal to CT naught plus T minus T naught times C prime T naught. Okay. So C prime T naught is the direction and that we just studied. So it's tangent to the curve, and CT naught is where your line touches, right? So this is your curve at CT naught. This is the direction of C prime T naught, which is the velocity vector, and this is the line. So what is the equation of this line? Equation of this line is given by this. You can see that when at t equal to t naught, you are at this point. Otherwise, you are at various points on this line. Okay, so let us look at an example. So suppose a particle follows the path which is described by this. until it flies off on a tangent at t equal to 1. So till t equal to 1, it's following the curve, and at t equal to 1, it flies off at the tangent. Question is, where is it at time t equal to 4? So for this example, we first need to figure out what the tangent line is, right? So what is the position at t equal to 1? It is the value at at t equal to 1, right? Where you are at t equal to 1. So at t equal to 1, you put t equal to 1 here, you get this, right? Now what is the velocity vector? It is given by et. You differentiate each component with respect to t. This is what you get. So what is the equation of tangent line at t equal to 1 from the previous slide? It is given by Lt equal to C1 plus t minus 1 C prime 1, which comes out to be this, right? I have just substituted C1 and C prime 1 from the previous 2 points. Hence, at t equal to 4, so see, at till t equal to 1, you were on the curve, but then after t equal to 1, you are on the tangent line. So on the tangent line at t equal to 4, where are you? So when t is equal to 4, you are at L4, right? Which is just substituting t equal to 4 here. This is what you get, and this is the answer. So this is the position of the particle at t equal to 4. So remember, initially it was traveling on the curve till time t equal to 1, and at t equal to 1, it flew off on the tangent at t equal to 1. And you had to find its position at t equal to 4. So you evaluate the tangent line first and then put t equal to 4 and calculate where the position is. Okay, so let us stop here.